and I'm going to have the first 7 digits of this infinite string, something like this now: 4, 6, 1, 9, 2, 8, and this one will be I'll let it be 6, 5, 0, 9, 3, 7. That's enough to give the idea. Now, when Merle constructs her number here that cannot be in the list, she does it like this. She makes the first digit of her number different from the first digit of the first number in the list. The first digit of the first number in the list is 1. So she starts her number that she's constructing with a 2. Now note that it could have been a lot of things besides 2. It could just be anything but 1. So that right away shows that there's going to be any number of constructions here. Now, so this is known as Cantor's diagonal proof. So we'll circle these numbers now. Now the second digit in the number that Merle is constructing, the second digit in the second number is a 6. So she puts a 9 there instead of the 6. So she goes to the third number, and what the heck is that? It looks like
0.
Well, yeah, you're right, it is 0. So she put something different up here, different than 0. Say a 1. Well, that's enough to give the idea that the reason it's called a diagonal proof is because these numbers form an infinite diagonal through the list. Okay. Now, say that the man that brings the list says to you, oh, well, this number that's being constructed here, let's say let's say the construction has been carried out plenty far enough so that he could claim this, because let's say you carry this out to 200 digits here. Let's say that he says, well, that number up there is the same as the 100th number in my list. And Merle replies, no, it can't be the same as the 100th number in your list, because the 100th digit of this number, whatever it is here, it's up here somewhere, is different from the 100th digit of the 100th number in your list.
Mm-hmm.
Just by definition. And that doesn't mean that this number that's being constructed is the only one that can be constructed that is not in the list, and for reasons I explained earlier. So this is sufficient to show that the irrational fractions are an uncountable, or as they say, non-denumerable infinity.
Mm-hmm.
The list can be infinite, but it can't include all of them, by far. And so, since it is infinite, but it's only the lowest order of infinity, that is, it's the order of infinity that's countable with the infinity of integers. But they call it Aleph null.
Mm-hmm.
Now, the irrational fractions cannot be counted, as this is intended to prove that. The irrational fractions cannot be counted because no list that purports to be the list of all irrational fractions can be upheld as actually doing that because it can be disproven by this method. Now, they call this second order infinity, the one that the irrational fractions are a part of, that order of infinity is called Aleph 1. And your book by Rudy Rucker will tell you all about that, and this is just the very beginning of it. And it gets to be more and more incredible as you proceed into the book. And the entire infinite series of Alephs, there's an infinity of them. Aleph null is the first one, then Aleph 1, I don't think I said that. I called one of them Aleph 2. Aleph null means Aleph 0. And then Aleph 1 is, then the irrational fractions belong to Aleph 1, which is non-denumerable, that's what they call it. And those Alephs go on for infinity, but there are beyond them, beyond the infinity of Alephs, there are other infinite numbers that are beyond the entire Aleph set. Can you imagine such a thing? But that's what mathematicians, that's one of the simpler things that they, from the time of Cantor, had proven way back toward the end of the 19th century. Cantor, by the way, had an enemy in the mathematical world that was so unkind to him, and I don't know, just Eric Temple Bell, I think in his account tells about it, that George Cantor ended up in a insane asylum because of the cruelty of people.
Kronecker.
Huh?
The professor's name was Kronecker. He was the head of the math department at the university where Cantor taught.
Yeah, you're right.
And caused him to lose his job.
Yeah, that's true. It was. I didn't know who he meant at first because as I said, I have a reader's vocabulary, and I always called him Kronecker.
Kronecker. And Kronecker, he didn't like Cantor rocking the boat with all this talk of the Alephs. He didn't like that because it was opposed to some of the ideas in Aristotle's logic that said the parts cannot be greater than the sum. And with Cantor's argument, you could have the parts greater than the sum.
Yeah.
You know,
have you? Did I give you a book? It was a book I meant you to have. Now I don't know if you got it or not, but it was called "The Adventures of a Mathematician."
No, I didn't get that. I don't think I got that.
That was written by
I would remember it.
Stanislaw Ulam, and anyway, he was one of the most important people in the development of the hydrogen bomb, along with what's his name?
Teller and Oppenheimer.
Oppenheimer
and Teller.
Well, Oppenheimer was the earlier
atom bomb.
Yeah.
It was Edward Teller that developed it.
Teller and Stanislaw Ulam both. But anyway, Stanislaw Ulam had contributed to advanced parts of this subject. This is called the theory of sets. That's what it's called.
I didn't know that, what you just said. I didn't know that Stanislaw Ulam had come after Cantor and made all these contributions. That was probably in the 1960s.
Well, lots of people have come after Cantor and contributed to this. But anyway, somebody on the forefront of all this was Stanislaw Ulam.